Watch Mr. Wizard. That's what all the kids in the neighborhood call him because he shows them the magic and mystery of science in everyday living.
Hi, Mr. Wizard.
Hi, Betty Sue.
What are all these Mr. Wizard's experiments in science doing here?
Well, I put them all up on the wall over there. You'll find out later. Here, come sit down.
Oh, thank you.
Because I have a problem there for you. See, here's an ice cube floating in water in a little dish and a string.
Yeah?
Well, I have a problem for you. I want you to be able to pick up the ice cube with the string without tying any knots and using only one hand.
You're kidding.
No!
Can't get in the water.
No success at all? Before you leave today, I will show you how to do it. In fact, it's a very nice little trick that you can play on your friends. Now,
that.
I will give you a clue. Over here.
All right.
See that sugar over there?
Yeah?
Would you get about, a quarter or half a teaspoon of it or so, and pour it here in this glass. And stir it up.
Okay.
Wasn't that a nice experiment?
What does it prove?
Well, you mean you've done this lots of times and you don't think it proves anything?
No, you're just putting sugar in water.
All right. If that's the case, where did the sugar go?
Well, dissolved.
What does that mean?
Well, it's sort of, the molecules of sugar broke up.
Why do you say they broke up?
Well, because you can't see them.
In other words, they were big ones, and now there must be little or something.
Yeah.
How could you prove that they're really there?
Well, is the water clean?
Yes.
Then I'll drink some. It's there.
Sugar water. Now, what I had you do this for is because you've done this many times. You've put something in water and seen it dissolve. Yet I don't think you really know what happens when something dissolves, and that's what we're going to investigate today. First of all, did the fact that the sugar dissolved in this water help you figure out how we're going to solve the problem of picking up the ice cube with the string?
Should it?
Yes, this should be a clue.
Well, I haven't seen it yet.
Okay, well, let us think then about other solids that will dissolve in water. In other words, disappear in water, like you say. Besides sugar, what else?
Salt?
Yes.
Tea?
Yes, certainly parts of the tea
when
dissolve in water. Yeah.
And coffee?
Certainly, coffee. Parts of the coffee, at least, because it colors the water. Any others? Most of the medicines that you take, if you take it by spoon, it's probably something dissolved in water.
You mean the syrup?
Yeah, various syrups, cough syrups and things like that. How about aspirin?
A's and the BBBs?
All the A's and B's? Well, obviously they're dissolving, right? So that's another solid that does. Now, how about other things other than solids? How about liquids?
That dissolve in other liquids?
Yes. Can you dissolve liquids in liquids?
Well.
Water and...
Alcohol.
Yes, alcohol.
Propyl alcohol.
Well, it's isopropyl. It's a certain kind of alcohol. Now, can you dissolve alcohol in water?
I don't know.
Well, let's try.
Stir it. It's dissolving. Yeah.
In other words, it's now spreading throughout the whole liquid. It's turned a little color. Part of that, I think, is air, which was dissolved in water, but we'll get to that in a minute.
Oh, okay.
Now, how could you prove that the alcohol had disappeared? Alcohol, evaporates. How could you prove that it just didn't evaporate? Handkerchief.
With a handkerchief?
Yeah, here. If I put it in here, I'm now going to wet it with the two liquids, right?
Alcohol and water.
The alcohol and water.
Mm-hmm.
All right. Here, you take this piece of metal. Hold it out there like that, because I'm going I'm going to squeeze out this handkerchief. So now put it over the end of this like that, and light it. Burning, isn't it?
Yeah, I'll say.
A little warm.
A little, yeah.
But the handkerchief didn't burn.
No.
What was burning?
The alcohol. And the water stayed on top of the handkerchief. Stayed on the handkerchief and prevented it from burning. Right?
Right. So you see now, we sort of separated the two out of...
Yeah. All that burned was alcohol.
Was the alcohol. So obviously the alcohol was there, because it wouldn't happen with water, would it?
No.
Okay. How about other liquids that dissolve in water? Can you think of any other?
Well, I can think of ones that don't.
Well, how do you mean?
That's any help. Well, like gasoline and kerosene.
And oil?
And oil.
Yeah. How about, well, probably you don't know about it. It's glycerin is another one that will dissolve in water. So you can dissolve liquids in water, too. Mm-hmm. Now, we have three different kinds of things, don't we? Solids, liquids, and what's the final one?
And solids.
Liquids, and finally, gas.
Oh, gas.
Can gas dissolve in water?
Well, air dissolves in water.
How do you know?
Well, because fish breathe water underwater. And breathe air underwater.
Yes.
And so it must be air in the water.
So the air is dissolved in the water. Here's another thing that you could have... Would you open that, please? And pour it in there.
Pour it in?
Yeah. Now stop right there. No bubbles here.
No, but there are bubbles
in here. Why?
Well,
pour some more.
Okay. Because the carbon dioxide that was in this water was released.
In other words, there must be carbon dioxide dissolved in there. Well, that's true. So you see, gases can be dissolved in water, too, and here we're having them come out.
Carbon dioxide gas.
Carbon dioxide gas. This happens in soda pop, champagne, beer. Carbonated beverages have carbon dioxide gas dissolved in them. Well, now, air and carbon dioxide both will dissolve in water, and some of it quite a bit, but ammonia gas. Have you ever heard of ammonia gas?
I've heard of ammonia.
Yeah. Well, ammonia is ammonia gas dissolved in water, really. And here's some of it right here. Here, don't smell of it directly. Just sort of pass your hand over and bring it over your mouth, over your nose. Ammonia gas is dissolved in this water. Now, what I'm going to do is heat it up.
The ammonia gas? Or the
ammonia water, which is actually water with ammonia dissolved in it.
Oh, and then the gas is going to come out.
Right. You can see little bubbles are starting to form. And we're now going to fill this flask with ammonia gas. Mm-hmm. Well, now, it happens that ammonia gas is very, very soluble in water. 800 parts of ammonia gas will dissolve in 1 part of water.
Goodness, that is a lot.
So now, when we have this flask filled with ammonia gas... Here, you want to hold that for a minute? What I'm going to do now, as soon as this is filled with ammonia gas, I'm going to take it off of here and put it on top of this stopper that has a eyedropper in it, so that I can squirt some water up into it. You notice the tube goes down into a supply of water. Mm-hmm. What will happen when you squirt a little drop of water up into this ammonia gas?
Well, the ammonia will start to dissolve in it.
Okay.
800 parts to each one.
Right. Now, if that... If the ammonia begins to dissolve in the water, what's going to be left in place of that ammonia?
Well, you're going to create a vacuum in there, because there'll be nothing.
What you're telling me is not sad. I'm crying. The ammonia's coming over. Right, we'll create a vacuum. So what will happen to the air pressure pushing down on top of the supply of water?
Well, it'll push the water up into it, up through the tube and into the bottle.
And we'll have a fountain.
Yeah.
Hold that a minute. Now, you can do this at home, but I'd suggest that you do it with the windows wide open, all the rest of it. Because
you can do it
with ordinary household ammonia will work this way. And you can now boil it up, but it sure gets, it's good for cold. Now,
powerful.
It sure is. You can see, obviously, that the ammonia gas is coming out of solution because it's in my eyes. I don't know about yours.
I'm glad on this side.
By the way, this certainly proves that there was ammonia in this solution, doesn't it? Because it's now in gas form and goes all over the place. Well, now you see there's some moisture up here because this...
Is that from the water that was in with the gas?
It's a water vapor sort of condensing on here, see? I don't know, you can't feel it, but I have a little cut right there in my hand. I can feel the ammonia gas comes up here and gets by the cut and is smarting. So I'm sure that there's ammonia gas coming out here. Well, let's try it. It may not go up as much as it should, but I'm getting tired of standing here and getting my eyes full of ammonia. So let's try it. Now, you squeeze the little ball down here, okay?
No?
Okay, go ahead and squeeze it.
There it goes. That's good. You can really see the ammonia.
Well, you can't see the ammonia, but you can see
when it's in there.
The fact that it is...
Look at that thing shake.
Well, it's trying to get more water than it can. See how much? In fact, if there were more water in there, it would probably go even further, but I didn't put it all full so we could...
Took all the water out.
Yeah, so we could see that air had to finally go in, too. Well, so now we see that solids, liquids, and gases all can dissolve in water. Now, would you come away from here?
Yeah, gladly.
Oh. I'm not sad. It's just that... Oh, boy. Now, what have we dissolved so far now?
We've dissolved solids.
Like?
Sugar.
Yeah, sugar and salt and so on.
Yeah.
And liquids?
Liquids, such as alcohol.
Okay. And finally?
And gases, such as carbon dioxide and air and ammonia.
And ammonia, okay. But now, what happens when these things go into solution or become dissolved? All we know so far is that they go into water, but what really happens?
Well,
You said before that they did what?
I said they broke up.
Well, that's very close. They break up in a very special way, however. Here, why don't you sit down? I'll bring up a fish tank, which is, see those things there?
Those yellow balls.
Well, those aren't little yellow balls at all. What those are water molecules. Okay. And here is 1 cube of sugar.
Oh.
Not a bowl full, because each one of these little black balls now is a molecule of sugar, and they're all clumped together in a little cube.
Mm-hmm.
Okay, now I'll put the clump of sugar into the water, and you stir it up.
Okay.
Okay, now what happens
Well,
when you stirred that up?
the sugar molecules went in between the water molecules.
Yes, and this is exactly what happened when something dissolves in water. The little cube or little tiny grain of sugar broke up into molecule size. And those little molecules of sugar now went in between the spaces in the water molecule. And that's where they go.
Oh, I see. But does it always have to be water?
Well, not necessarily. In this particular case, most of the time in this particular case we use water, and in most other cases we use water because water is the best solvent. In other words, things dissolve in water better than any other liquid. But there are some things that do not dissolve in water. You mentioned one earlier.
Oh, gasoline.
Gasoline does not. Now, in that case, you might use gasoline as a solvent for other things. For instance, a spot. Mm-hmm. You know, a grease spot from food. Mm-hmm. Well, if you try to get out with just plain water, it doesn't work very well, and you have to get soap and other things. So instead of doing that, you have what?
Cleaning fluid.
Well, a cleaning fluid is nothing more than a liquid that will dissolve this grease better than water does.
Oh, I see.
And that's how you can make it disappear. So it doesn't have to be water, but most of the time it is. Mm-hmm. And what happens now when something dissolves?
Well, the molecules break up, and they go in between the water molecules.
The molecules don't break up. Now, wait a minute. The cube or something breaks up.
The thing breaks up into molecules.
In the case of sugar, this happens.
Yeah, they separate.
Okay. Now that you understand this, you should also be able to understand that while it looks very simple, in other words, the thing sort of disappears in the water, it really is more complicated because you now have chemicals in molecular form. And this sometimes changes the whole characteristic of the solution. It's quite different than water by itself. And that's what should help you with that ice cube. Here, pull it back over here.
All right.
This was sitting here, and you didn't realize that this was an important part of the thing. Because what is it I wanted you to do? Go ahead, try it.
Well, you wanted me to pick up the ice cube with the string with just one hand and no tying knot.
Okay. Now, put the string right over the top of the ice cube.
Like that?
Yeah, right like that. Now, sprinkle some salt on top of the ice cube. There. Now, that's enough. Not too much. It so happens that when you put salt in water, it now changes the characteristic of water. What does water ordinarily boil at?
Is it
212 degrees Fahrenheit. Well, when you put salt in the water, it raises the boiling point. There's no longer boils at 212, but something above that. What does water freeze at?
32 degrees.
Yeah. Above 0 Fahrenheit. Mm-hmm. Okay, and when you put salt in it, it lowers the freezing point. It no longer freezes that, but at something below that, depending on what you put in and how much. So what we have done here is put salt on top of the ice cube, and it's now going to start to melt the ice cube.
Is that why they put salt on the sidewalk when it's snowing?
Right. Well, especially when it's icy.
Yeah. So that it'll lower the freezing point.
Right.
And then it melts it.
Right. So they don't have to, bother to chip it up and so forth. Now, that's what's happening right here. Now, in order to melt the ice cube, it has to get heat from someplace, doesn't it?
Yes.
Okay? So in this case, it's getting it from the water that was on the string, which does not have as much salt dissolved in it. So if it takes water away from the ice, from the water on the string, if it takes heat away from the water on the string, what's going to happen to the water on the string, maybe?
It's going to freeze?
Well, try picking it up slowly.
All right. There! Hey, that's terrific.
No knots, right?
No knots, no anything.
No anything. And you
Except
were
the salt.
except the salt, that's right. So this is how you can do the trick, because now you can now add things to water and lower the freezing point. What happens, by the way, in the winter, or in the summer, you have water in the radiator of the car.
Yes.
What do they do in winter?
They put an antifreeze in it.
Yes, which is nothing more than a solution that freezes at a lower temperature than water does.
Oh, I see. Mm-hmm.
So now scientists can design all kinds of liquids to do all kinds of things as far as freezing by simply combining the right kind of ingredients in a solution. Well, now it looks like it's a simple problem of simply putting salt in water, that it now will lower the freezing point and raise the boiling point and go into molecular form, but it's a little more complicated than that. Here, let me show you over here. See that soda bottle over there? Would you move that out of the way?
Okay.
Now, see those two sticks? Would you hold them on those ends there? See there are wires on the end?
Yeah.
Now, I want to plug it in. Just a minute. Turn it on. You touch the two together.
Rings the bell.
And what you've really got here is nothing more than a switch, because current comes from the transformer, through here. When you touch, it'll go across here and ring the bell and come back here again. Mm-hmm. So as long as you keep them separated, the bell won't ring. Touch them together, like a switch. Okay. Mm-hmm. Now, water. Put the thing in it. Does it ring?
No.
Touch them together once. When you touch them
when
together,
you touch
it does. But now the water is not a conductor, is it?
No.
Okay. This is true. Ordinary, nice, clean water is not a conductor of electricity. Let's add some sugar. Stir it up a little bit. Nothing happens, does it?
No. Okay. Same as just plain water.
In other words, a sugar solution does not... Whoop, you went and touched the two together. Sugar solution does not conduct electricity. Now, here's another glass of fresh water. Put this in there and see if it rings. Does not. Okay. No. Now, let's put some salt.
Should I stir it up?
I see how it's beginning to conduct.
Yeah. Salt is a good conductor.
Well, it's getting better and better, too, as it more and more dissolves. Okay, now let's turn. Why is that now? Theoretically, you can touch it now. I turn the switch on. Why is it that when sugar, when you put it in, does not conduct current, and yet salt does? There must be more to it than a simple dissolving and going into molecule form, isn't it?
Yeah.
Well, let's see if I can explain that. Come on over here. Because I have a sort of a homemade version of what we have been talking about. This is a glass of water.
Here's the water.
And here's the top of the water. And here are the two wires, here and here. Yeah, the two sticks that you have. Notice these little things here. These are magnets which you can take on and put off. Mm-hmm. These are electrons. Oh, yeah. See, a flow of electricity is a flow of electrons. Okay. So these are electrons, but they're stopped here. They can't get across because this is water in the first place. Now we put sugar in it. And sugar stays in molecule form and goes floating around. Touches these.
And it doesn't conduct.
Nothing happens. Now we put salt in. When you put salt in the water, a very strange thing happens. Not only does it break up into molecule form, but it has plus and minus charges on it. Positive and negative charge. The sodium part is positive, and the chlorine part is negative. And it can go floating around. And here, see all these negative charges? Yes. They would attract this positive part over here like this. Uh-huh. And what would happen to the negative? The two negatives, what would happen to them?
Well, that should repel this one.
Right, so you repel it over that direction.
Over here?
Okay, yes. Okay. When that happens, this little negative part can jump off over here. So it does. At the same time, one of these electrons is jumping over here because it's attracted by that positive. Now this is neutral, and it goes floating around, and that's neutral too, isn't it?
So it goes floating around? Yeah,
so they would finally come together again.
When you'd have a salt molecule again.
Yes, and now watch what happens. This negative charge would go over here and go onto there, and it's now as it was before. Now, as it would be dragged over here again. Now what'll happen?
And this one's repelled.
Same thing all over again. I'll put another one over here.
And this one comes off here.
Okay, now they get together again.
And then this one comes on here. And it starts all over again.
The whole thing starts all over again. Now, this is called ionization.
Ionization?
Yes, because these are electrons, And when this molecule breaks up into two parts, these are called ions. I-O-N-S, ions. And this is called ionization, this process. You can see the net effect is eventually these electrons flow over to here, and we now have what is an electrical current flowing across there.
Oh, I see.
So some chemicals do not break up into ions. That's what sugar is. Other chemicals do break up into ions, like salt. Other chemicals like sulfuric acid do, and all kinds of things. Salt of most kinds do. Let's say it's a silver compound, that instead of this being Na, sodium, it is now salt. When it's over here, this plus charge, scientists can work it in such a way so that this would get stuck over here and stay on here permanently. And if this were the inside of a spoon, and this were silver...
It would plate it?
Yes.
Oh, but I always thought that silver plate was dipped.
Oh. Put on here in this process of ionization, or electrolysis, it's called. In other words, the problem of running electricity through a solution. And that you can now have silver all around the spoon or knife or fork, and you have silver plating. And this is silver, copper, chromium, nickel are all put on like this. Yes. So you see, it's not quite as simple as that. But now that you know that things can break up here into molecule form, this should help you understand that chemical reactions can take place a lot more easily. Here, would you move that stuff out of the way? I'll bring this stuff down and you'll see what I'm talking about. Here, I'll put them over here. Won't you sit down?
Oh, okay.
Because here, put about half a teaspoon of this in. Yeah.
Oh, here.
Yeah. What is that?
Bicarbonate of soda.
Right.
Is this enough?
That's enough. Okay. That's one chemical. Now hold the spoon over the top of it. I'll sprinkle in a nice good supply of this other chemical. See what that is?
Cream of tartar.
Cream of tartar. Dump that in. Stir them up. See anything happening?
No, should it?
Well, now, this cream of tartar is an acid, and the baking soda is a base, and when the two get together, they should react. Nothing happening, is there?
Well, maybe because they're two solids, and we didn't learn that two solids could...
Try putting some water in there so they now can dissolve. Fill it all up with water.
Okay.
Stop.
Wow, look at it.
Obviously, something is going on in there, right? Now, you see how chemical reactions can take place more easily when things are dissolved. And you see why? What would happen now when you had the two solids together? Were they in molecule form, really?
No, they weren't broken up.
They were little powder form, weren't they? So when you now have them in solution, they can break up and react easier. Now, remember that, because that will help explain this next thing. See these two glasses?
Yes.
Well, these two glasses have chemicals dissolved in them.
They're water with something dissolved in them already?
Once something is dissolved in there, and something is dissolved in there. When you put the two together, a chemical reaction takes place. Okay? Pour that one into there.
I don't see anything happening.
Oh, well, watch. Did you see that?
It's amazing.
Isn't it? All of a sudden it turned dark, didn't it?
What is that?
Well, this is a special kind of chemical. Here the two are, two more.
Let's do it again.
Well, we'll do it again, but just I want to explain to you what happens. This one is one that has a starch solution in it. And this one has an iodine solution in it. And it's one of the standard chemical tests. When you put starch and iodine together, they turn dark. But this one, this solution over here, the iodine is not free to react with the starch yet. A certain amount of chemical reaction has to take place between one of the ingredients in here and one of the ingredients in there before the iodine is liberated.
Is that why it took so long?
And that's why it took so long. Now, this one I timed out took about 7 seconds. And you can time it by diluting it. The more you dilute it, the longer it takes. I've diluted this one now so that it takes about 12 seconds. So theoretically, when you pour this one into here, by the time I count to 12 or 12 seconds, the change should take place.
All right.
Try it once. Go ahead.
Which one should I pour in which?
Doesn't make any difference. Are you ready?
All right.
Okay, go ahead.
Go.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Go!
It went.
You see, because it was diluted and wasn't mixed, you see how it was a little more gradual this
that one
time.
went really went fast.
Anyway, it's kind of a spectacular chemical reaction that kind of typifies chemical reactions that take place when?
when things are diluted.
Not necessarily 12 seconds.
No.
When things are diluted, that's right. And what else do we find was important about solutions?
Well, they make chemical changes.
Like this?
Yes.
And besides that now?
Well, it does different things to the... Well, for instance, take water. If you put salt in it, it changes the freezing temperature and the boiling temperature of water.
And that can be very useful, too.
Mm-hmm.
And what else?
And, let me see.
How about conductors and non-conductors?
Oh, some things are like salt is a conductor, while sugar isn't, because it's ion. It's an
ionized, yes.
Oh, it's
because
ionized.
Salt ionizes and sugar does not. Well, very well. Now, you now see some of the importances of the solutions. Now, you asked me about those Mr. Wizard's experiments in science that were up on the wall. Well, come on over. Let's take a look at them. Because I put those up there because I'm now planning the issues for 1959, see? And here are the issues that we sent out in 1958.
Yeah, they were all great. I enjoyed.
Did you
They
like
were
them?
so much fun.
Good.
There were a few that I liked especially.
Like what?
Let me see. Oh, here, this one with the comb, where
Yes.
you charge it, and you put the thread down.
You charge the comb, you mean you rub it on some wool.
Yeah, that's right. And then the thread comes out like a snake.
Yeah.
And then let me see what other one. Oh, this one here, where you could play music, like a pipe organ, in a little tube if you put water in it, and you blow over the top of it.
That was a whole issue on sounds, wasn't it? Music, yeah.
And let me see here. What else?
That first issue was on what? Static electricity.
Oh, and this one here.
Oh,
where
yeah.
You put the nail and the thread in the bottle, and you put it in the sunlight or something, and you put the magnifying glass in front of it, and pretty soon you burn a hole through the thread.
Mm-hmm. And down it goes.
And down it goes.
Yeah. That was a whole issue on light.
And on the front of this one, there was a cute one.
Well, let me see. This is a whole issue on plants now.
Oh, here. You see, you put the seed in between a blotter, and you wait for it to sprout. And then when it sprouts, you turn it upside down, and you see that it grows upside down again. And it keeps going backwards and forwards again.
You can have a lot of fun doing that. Well, anyway, I'm glad you enjoyed these. Actually, there were about 30 in each one of the issues. And of course, next year, there will be about the same number of experiments in each one of the issues. There will be 8 in all.
What are you going to have in them?
Well, I don't know. I'm in the process of planning them now. We're going to have one on the human body, which I think should be fun, how it works and whatnot. Another one on water. We may even use some of the solution stuff, you see, so that kids can do that, too. And we'll do one on surface tension. Oh, here's one surface tension. You take some of the stuff that's in this tube and put it on the points of this toothpick.
You open this, please.
And then, once you've got it on the toothpick, drop the toothpick on the water here.
Look at that. It swims.
Yeah, it looks like it's alive, doesn't it? Well, that's because of a thing called surface tension.
But what's this stuff?
Well, I don't think I ought to tell you. I think I ought to wait till you get the issue of Mr. Wizard's
not fair.
experiments in science on surface tension. That'll give you the idea of the sort of thing we're planning for next year. So, anyway, if your friends have been getting these for 1958, they're not going to get those for 1959 unless they send in a new subscription. So have them send their name and address and $1 to Mr. Wizard, Box 139, New York 10, New York.
All right.
If you have been receiving Mr. Wizard's experiments in science during the past year, it is now time to renew your subscription. Send $1 with your name and address to Mr. Wizard, Box 139, New York 10, New York. You will receive 8 new issues beginning in February 1959. Each issue contains fascinating experiments you can do with things you will find around the house. To be sure you continue to get your copies of Mr. Wizard's Experiments in Science for 1959, send $1 with your name and address to Mr. Wizard, Box 139, New York 10, New York. Watch Mr. Wizard is presented by the Public Affairs Department of the NBC Television Network in cooperation with New York University.